0.00120968T, and then divide by I'm missing a 0. 0.000 42,862, roughly. 42,862 is approximately T. Look, it's years, so I mean that's close enough, right? If you said 63, that would be okay. You know, I think if we're within a few years, we'd be okay. Yeah, it was exactly August 5th, 3:30 in the afternoon. It was raining. Right. It was raining. He fell, hit his head.
Exactly 43 minutes on the clock.
All right, get a basic idea of how that works? So this is actually what is used in some they don't always apply carbon-14 because if it was relatively like if the person died 3 hours ago, you don't use this because half-life is so long that you wouldn't be able to get it nailed down. I mean, we're happy with this carbon-14 being within like a decade or 100 years. Yes?
So are we going to have to memorize the half-life of carbon-14?
That would be something I'd provide you. So whatever I gave you a problem for, I would tell you the half-life is blah. And then what you do is first go get K. Once you have K, you set up your master formula. Then you just solve the rest. K. Understand? Okay, we are going to review in just a minute, but I always like to talk about this. This is it. That's all that would be on the test. I give you a word problem with some half-life of something, and then you. What formula?
This formula.
How about I say, like using this formula and a half-life of this, but you still have to like.
Okay, that'll work.
That okay? I'm not going to tell you what T represents, and
you
just the formula.
Yeah, just the formula.
Yeah, with K, right?
Yeah.
I'll give you that. But on the final, try and memorize.
Plug everything in and what it means.
Okay. So one of the reasons I like this topic. How many of you have heard of Chernobyl? Oh, good. So what was Chernobyl? What is Chernobyl? It's still there.
It's there was a nuclear meltdown at the Chernobyl nuclear plant. They had to evacuate the whole thing. They can't even take pictures or get inside it because it's so radioactive. They actually got a picture of the reactor by putting a mirror through several mirrors to get a picture of the actual.
Oh wow! So you were there. You sound like you were there.
No, I've done a lot of research.
Oh, cool.
It was one of back in the day I did a research part.
I forgot what show it was, but it was like somebody going out in outer space. They're like, "Can you sure you can trust Russia?" And I was like, "You can trust them as good as the people who brought you Chernobyl."
Yeah. I'm looking up something real quick.
But yeah,
that's in reference to what we're talking about.
Yeah, and you can only spend so much time there. They're only allowed to spend so much time there because it's radioactive.
Okay, so from what? Hold on. All right, well, okay, this is just a real quick Google search on this. But yeah, there was, nuclear reactors, they use some radioactive element to create energy. If they lose control of that, they lose control of the temperature, and that's what happened, then it basically gets like temperature, like core of sun temperature type stuff, and it basically melts through everything like butter, and there was explosions, it emitted, ejected this radioactive material. So there was a real bad situation, and even to this day, it's still uninhabited, But people are starting to get closer and go back, but it's kind of like a campfire that's been burning for a while. Well, anyone know how much bad stuff actually, like how much material actually they lost control of?
Several times. Several times.
Okay, several times.
I can't remember right off the top
From the research that I've read,
Approximately
it's
1
10
pound.
pounds.
How many?
10 pounds.
Yeah, it's not a lot because you're
Ten
eating.
Yeah.
Well, no, because, but then when it all like went bad, then the whole.
Yes, I understand, but initially,
Oh,
The
yeah.
radioactive
what they lost
material.
control of was like 10 pounds of bad stuff, of uranium. Then everything else got contaminated.
It was funny, it was kind of like with the World War II thing when we were interviewing the whole German scientists, because we had the atom bomb. We were like, well, how much material do you think we use? And they're like, well, I don't know, probably a couple 100 pounds of the stuff. And they're like, nope.
No,
couple
it's
pounds.
like right here. Look, I got it in my back pocket. Yeah.
And
So
they
it's
didn't
not
believe
much.
it.
It's not much. And so the reason I like to bring this up is because the half-life of the stuff that's bad, from my initial little look on Google, but I thought it was longer. It's saying the half-life of this stuff, the stuff that's causing the gamma radiation that you can't live around, is 30 years.
It's already been like 50.
I don't know. I think it happened in the 80s, right?
Early 80s.
So let's just go with 30 years. It seems like it should be longer, but let's go with 30 years, okay? So whatever this bad stuff is at Chernobyl has a half-life of 30 years. So I know this. Half of what was there initially, right? Initially, I'm assuming all of it was there. This is 50% of it will be K times 30. Do you understand what I'm doing here? Trying to figure out what this decay constant is. So this, I come in and I do natural log on both sides. Natural log of 1/2 equals 30K, right? Because the E and the natural log kill each other off. And then I get on my calculator, I take natural log 0.5, and I divide that by 30. And I get negative 0.0231. I'll go with that is K. So for the Chernobyl, situation here, the amount of bad stuff there is the amount that was there initially times e to the negative 0.023 K, right?
It's not T.
T, thank you.
I was about to say,
T.
that is K.
T. So how much was there initially? I just told you 10 pounds. So let's say that this was 10.
10 to the E.
So that would be our formula. Right? At time equals 0, right? At T is 0. This all goes away and turns into a 1. And we had how much was there at time equals 0? 10. My question is about how much is there now?
Quick question now.
Yes.
So when we read the problem the first time to find K, we don't put that 10 there.
No, we look at that number here as being a
Second-
percentage.
Second time.
The second time, you can put how much is there. Okay, so this is going to give you how many pounds of stuff is there at the end.
Right.
Okay? The thing is, look, even if you had come in, you remember when I put half and I put 1 and I put e to the whatever? Okay, if I would have put 10 here, what would I have to have put over there?
Divided by 10.
Well, yeah, half of 10 would be 5. And then when you divide by 10, you would get 1/2. And this 1/2 will always be the case. Even if I started out with, 200 pounds, then this would have to be 100, and then I divide through. This is always going to be 1/2 when you're doing a half-life.
So just might as well just go ahead and cut off.
Just always use 1 and 1/2 when you're trying to get K. Good question. So my question now is about how much of that stuff is still there. I think this happened back in the 80s. So let's just round up, okay? Let's say that this is about
Let's just say 80, so
40, 50 years.
it's not even that.
I mean, what do you want to go? 40 years? Let's go 40 years.
40 years.
So in 40 years, how much will be there? So what is A of 40? So 10 e to the negative 0.023 times 40. See, I'm plugging in t as 40. I'm not setting it equal to 40, right?
Because it is a number.
I'm plugging in the time, 40 years. So I'll do that on my calculator real quick. I'm going to multiply these two together first. 40 times, and then I'm going to take e to that number, right? E raised to that. and then times I screwed up.
Alright, and then
0.92. So when I do all that, I get 10 times, and then all of this, E raised to all that, I'm getting 0.3985 something. Anyone else getting that?
Yeah.
Yes? Because this is a negative number, E to a negative number. And then you multiply that, you get 3.985
Yeah, that's what I got.
pounds. So 40 years from when it happened, there's still a little over half
Half of it's still there.
of it's still there. I mean, a little under half of it's still there, right?
Still gonna be inhabitable for like thousands of years, right?
Yeah, because when you think about half-life, it never truly goes away. Think about the paper being torn. Now, there might be an amount that's there that's so small it's insignificant. That's kind of the way drugs work in people's bodies. You know, there might be initially like chemotherapy, like radiation therapy and things like that. That half-lives are much shorter than 40 years.
Well, that's why they have.
But it goes to an amount that's not measurable anymore, and so it's basically not having an effect on the body.
So
Yeah.
that's why when you have to take your antibiotics like twice a day or whatever it is,
Mhm.
because the antibiotic is only effective for so many hours.
Yeah.
So it's
And it gets filtered out by your body naturally. So that means no one's going to Chernobyl anytime soon, even though it is decaying out.
better, not as bad, still bad. Well, it's funny. My uncle.
That's funny. Chernobyl's funny.
No,
No, I'm kidding.
What's interesting is my uncle is a physicist.
Uh-huh.
And he works alongside engineers. And one year he took a contract with the state of California to do soil testing. And they were testing the soil samples because when we bombed the Japanese back in the 40s, some of the radiation had gone along with the what do they call those things? The Gulf Stream, and it deposited some of the radiation in California, which is why a lot of California is still owned by the federal government, radioactive in some form.
Yeah, usually when I talk about Chernobyl, I talk about, the thing that alarms me is not necessarily the 10 pounds of the really, really nasty uranium. It's all the byproducts of the Cold War. When we were having that big pissing contest with the Russians and building all these nuclear weapons, and basically we got to a point where, to make nuclear weapons, you create byproducts that are bad. And so we got to a point where we were filling up tanks, containers full of bad stuff, and that stuff's all over the place still.
Well, the way they got the uranium-235 back in World War II is they used silver, like silver bullion, to process the uranium to that specific uranium isotope.
Let me get by you one more time.
And to do that, now we have like tons and tons, literally, like millions and millions of dollars of radioactive silver from processing it.
Did y'all ever hear about, I forget which Bush president it was, but they had this plan, because what we had is, again, back in the Cold War, we had these huge vats, concrete vats that held like thousands of gallons of this like soup, this nuclear byproduct soup. And they were huge concrete containers that were put into the ground, and they just poured this stuff in there, and they really couldn't even explain like what it was. It was just like really bad. They said, I think they took a sample and they said, like, if you just put like 1 cup of it in this room, and like we were all in here for this class, for an hour and 40 minutes, like we'd all be dead within a month. It would just take a while, but whatever was in there would mess us all up. So these containers were starting to crack. The concrete was starting to, not be able to hold this stuff. So they wanted to do something, because they put these right next to a river, and it was going to get into the drinking water. It was just real bad. So what they decided is they would take this stuff and put it into a mountain, like deep into a mountain, because mountains are geologically stable. And the mountains in the United States, the mountain chains are considered to be geologically stable, at least for some period of time. And so they wanted to get all this stuff into the mountain. Well, I believe this stuff was out in California. And
That's when my uncle was got his contract.
trying to get this stuff. So I think one of the Bushes, I don't remember which one it was, had this idea of, well, we can't transport this. They wanted to put it on train and take it. But you can't, if you spill a liquid, I mean, that's it. You spill it, you're not picking that up, right? So the idea was to take the liquid and convert it to a solid. So if, you can convert liquid to solid, so they're like, well, let's convert it to a solid. And they figured out that there was a way to do it, and they started to do it, and they put it into this factory, and they go through and they spit out a solid on the other end. Then they could put that on a train, and if it falls, you pick it up and you put it back on the train. Pardon?
So they made nuclear pops?
Yeah, it's like nuclear popsicle sticks. And but the problem they ran into is that in the process of converting it from liquid to solid, that it was emitting a gas out of the factory, and that gas wound up being just as bad as the stuff. So you really can't contain gas, and so they shut it down. So this stuff, as far as I know, is still sitting around, just waiting. Yeah. So.
Yeah, these concrete containers.
Yeah, kind of like that, but it'll kill you. This stuff will kill you.
Ryan's just
Yeah,
sitting in tub.
just sitting there. Yeah.
Oh, let's pour it on the roads. No, I'm just kidding. Let's not do that anymore.
Well, again, the thing that scares me is not this part, because the U.S. at least we have it in containers. It's the Russians that when the Russians did it and their empire fell apart. Where's all their stuff? Where's all their byproducts? And I've actually seen in my life videos of crews in Russia, these groups, these guys that would go and they would have the little radiation meters, things like Geiger meter things, and they would actually go around in trucks out in the woods in the Soviet Union or former areas of the Soviet Union. They'd be driving around, and then they would look, their meters would start going off, and they would go try and find this stuff, and they would find these byproducts, these solids, and they would have these like huge tongs, and they'd go out there and they'd pick up this stuff, and they would run it back to the truck, which had this big like lead drum in it or something, and they would try to throw it in there. And so they would be running with this radioactive stuff, and there would be a guy back at the truck timing him, and he would blow a horn to let him know that's it. That guy's out for the rest of the day. Like he can't touch anymore. And so another guy would come in and pick up the tongs and take it the rest of the way, and then burnt, horn, time's up, next person would come in. So you couldn't overexpose yourself. And so you're doing that, and that's just one little piece of bad stuff, and who knows how much. That's what's always concerned me, is that you get the wrong people get their hands on this stuff that's laying around. That to me is like the biggest sort of threat that we have.
They can't even touch it, so.
I'm pretty sure they're willing to, people are willing to sacrifice themselves for that. Anyway, okay, we're going to not get too off track here.
This is how Donald Trump's going to kill us. All
Yeah, just gonna open up a tank that goes down into Mexico, or a little hose that goes down.
This is why we can't let Donald Trump be president.
I think you'd get a gas then.
We use it for extermination purposes.
All right. If you go to our course in Canvas, which everyone has access to, right? And you go to Files. This has been in here all semester, by the way. And you go to Old Stuff. And you go to Exam Review and Exam Solutions. And down here is Exam 3 Review from Fall 2013. And I was looking at this thing and I thought, you know what, this is a really good review. So I thought that's what we would kind of work on today, like for the rest of the class. Should we just go through it first and look at it? And then, okay, and then we'll kind of pick problems. I'm going to download it. So you can just download this to your computer. You can open it up and print it out at home, whatever. This is a reasonable approximation of the difficulty, scope, and format of the exam. It is roughly twice as long as the exam. However, it is not intended to be your only study guide. You should practice additional problems. In other words, make sure you've done your homework and you know how to answer those questions, and make sure you follow along with the lecture. By the way, this is not my review. This is Amy Collins, who teaches this class also. She was kind of like the lead instructor for this course, so she put together reviews. I'm using this. All right, so let's look at this first one. Determine if the following functions are exponential. If it's exponential, to determine if it's growth or decay. Do you want to try and knock that out real quick? Okay, let's just look at it. How about that first one? What's the base of that exponential function? 4/3. Okay. And do we have growth or decay?
Decay.
Why?
Because the negative exponent.
Okay, so we have to be a little careful here. You're right, but 4/3, right, to the negative 2x, 4/3 is bigger than 1, right? Which would tell you exponential growth. That's what that means. But a negative up here does what? So exponential growth goes like this. But a negative up there flips it, reflection over the y-axis makes it do this. Remember, a negative up in the exponent will be a reflection over the y-axis. So that would be negative, with me? So that's growth, that's exponential decay. How about the second one? Is it exponential? No, that's log, right? So that's not. How about x to the pi?
Yes. Because it's still 1. So
Where's the variable? In the base or the exponent? In the base. All exponential functions, the variable's in the exponent. So c is not exponential. Right? That's like x squared, except instead of squared, x to the pi. Pi is a number, 3.14. You all with me?
Right.
How about d?
That is growth. Growth, because you're going to take half of the 100, which is going to be 50 to the x. So 50 to the x.
Okay, can you multiply 100 times the half first? No, why not? Order of operations, right? Order of operations, you must do exponents first. So the 1/2 to the x is the first thing you do. And you know what? This is actually really bad notation. I never caught this before. This should be in parentheses, or else that x is only on the 1. Okay, 1/2 to the x, I think that's what we mean to be doing here. And so that means our base is less than 1, which tells us we have exponential decay. The 100 out front, all that does is stretches it. So that doesn't have the effect of flipping it, like the negative did on that other problem. So this would be exponential decay. All right? How about the next one? Exponential decay. So if it was e to the positive 5t, that would be exponential growth, but because it's negative, again, it's going down. This is like negative k, isn't it? Like on the problem we just did? Okay. All right, how about this? Evaluate each expression using the graphs. Where are we? This one's kind of tricky, but there should have been a homework like this.
Yeah, there was, but there weren't any. I don't think we had to find like inverses of those things.
No,
Okay, so let's try this. You mind?
actually, we
Okay.
Well,
Oh, you're
that
okay.
was different.
Let's look at the first one. We want f of g of 6. So this means that 6 goes into what first? G. So come over here, look for the g function, which is this one.
Yep.
And you know what? I think I'll flip my camera around just to have this. I don't think it's going to come out very good because of the reflection off that, but yeah, it's probably not going to come out at all. Well, it's better than nothing. So we go to the g function. We plug in 6 first, right? So, pardon? I've tried that in here before. It doesn't work. It's the glare of the projector. It's almost perfect. It comes off, it glares off the board, goes to the camera. The only way to do it is to lift the camera up
But I feel like
really
at a
high.
different angle, like, you're-
Trust me, I do my Cal 3 class. I record myself right here on this board. I've tried every variation. There's only one way to do it, and I don't want to set it up. So, okay, plug in 6 to the G function. You get 5, right? And now take that answer and plug it into F, right? Everyone understand what I'm doing? F of G of 6, right? So the answer that comes out is 5. Now 5 into F. Where's F? This is F. So you plug in 5 to F, and it spits out 1. So the answer to the first one is 1. What's G of negative 1? So negative 1 goes into G first. So here's G. Plug in negative 1, and spits out 3. Now take that answer and plug it back into G again. So here's 3. You get 1 out. So that's 1.
Now, do we have to show the steps?
No, you don't have to show any steps. Any questions? Okay, how about the next one? F inverse of 3. F inverse of 3. So here's the way you can visualize this one. We have a domain and a range, and F goes this way, right?
Right.
F inverse goes this way.
Right.
I want F inverse of 3, right? So 3 goes back to something. What over here goes into F to spit out 3? What goes into F that spits out 3? So go to your F function, which is this one. And where does this thing spit out 3?
At 7.
At 7, right? If I plug in 7 to F, it spits back 3. So that means this comes from 7, doesn't it? So going back, 3 should go back to 7. So this should be 7. It's just backwards. It's asking you to look for the ordered pair on here where the y coordinate was 3 on F, and then spit back the x answer. No? I'll give you another one. What's G inverse of 4? Ooh, God, that's not good. Because there's 2 places, 3 places. There's more than one place. Do y'all see what I'm saying? Because the G function,
You do G inverse of 1.
yeah, that's about the only one I could do, right? G inverse of 1, which would be 3.
But if you did 4, wouldn't you say it was 5 and 1?
It would be 5. Well, see, this doesn't have an inverse because it fails the horizontal line test. But okay, I hope you get that idea. How about the next one? F of F inverse of negative 1. Ooh, this is weird. You can make this a lot harder than it has to be. What happens when you put a function together with its inverse? They just cancel out.
So it's negative 1.
It's just negative 1. Right? This is like natural log of e of something. They just kill each other off, and then you just get that. Now, you could check it yourself, but do y'all want to check it or no?
No,
No.
it's no point because you're just going to get 0, 0.
No, you're going to get back.
You're going to go back to negative 1.
Well, I would just use that as an example.
Okay, that's it. All right, for these 2 functions, find fog, f of g of x.
And it's the main.
We did a couple of those in class, didn't we? And the domain. So do you want me to do this one right here, or do you want me to move on?
Just plug the
First of all, it would be
G, so it's going to be 3
It's f
x.
with g inside, which is f with g, which is x over 5 minus x. Oh, this is an ugly one. Then you're going to take that and plug it into f,
Which is 3.
which 3 of those, and then x right. Ooh, that's 3.
X over 5 minus x plus 1, and then go all divided by x, x over 5 minus x, again, minus 3. So you're going to need to solve for each side.
You're gonna do like a common denominator. First, I'm gonna do this 3 through here. So 3x, it's just gonna go to the top, right?
Yeah, and then 5 minus x plus 1.
And on the bottom, Nothing I'm really going to do here. So we need to put the top, we need to put those two things together, and the bottom, the two things together. So common denominators, 5 minus x. So this will become 3x plus 5 minus x over 5 minus x over x minus. You have to be really careful with that though, right? Do y'all see what I'm doing? 5 minus x, top and bottom, 5 minus x, top and bottom, and over 5 minus x. These flip like this. So when I flip, it's going to be a 5 minus x on top, and then this on the bottom, right? X minus 15 plus 3x.
In the book, they don't distribute it, they just leave it like that.
Yeah.
Oh, that's fine. That's fine. I'm just doing that.
And then so it's gonna be 3x plus 5.
3x plus 5 minus x, that's 2x plus 5 over 4x minus 15. That's it.
But the domain,
Yeah, that's fair.
That's it.
That's a fair
well, don't you have to find the domain?
Okay, what about the domain?
So the domain can't equal.
You have to go to g of x first. And
Yeah, x goes into what first? G,
Yeah.
which is
It cannot
this.
equal 5.
So you know from this right away x can't be 5, right? X cannot be equal to 5. Then that gets plugged in over here and turns out to be this, right? 2x plus 5 over 4x minus 15. And you know that the bottom of that can't be 0.
Right, so you can just solve for that and see what that is.
So 4x minus 15 cannot be 0.
15 over 4.
15 fourths cannot be there.
So I don't know what that is in normal language.
It's a little less than 4.
So you're gonna do negative infinity to.
Any questions? I'm going to write the interval, but any questions on that domain? Okay, so it'll be negative infinity to, let's see, which of those comes first? 5 and
15 over 4.
15 over 4 will be the first number.
And then union 15 over 4 to 5. And then union 5 to infinity.
There we go. So you're just skipping those 2 points. Question?
Would the 15 over 4 be a bracket?
Do what?
The 15 over 4?
No, it can't equal.
Yeah, if it is equal to that, then we get division by 0. So we don't want that one there. All right. So y'all felt okay with that?
Yeah, that one is fairly straightforward.
You just got to be careful with that algebra in there. All right, next one. Sketch the graph, state its domain, and find its inverse. I would only want you to sketch the graph.